Assalamualaikum and good day to all lecturer and to panel. So today I would like to present my final year project entitled Design and Analysis of Piping System for Turbine Cooling Water System. So I am the presenter. My name Afezah binti JAINUDIN. So basically today contents outline consists of introduction, summary of literature review, methodology of research, result analysis, as well as conclusion. The demand for green energy production is currently arising all over the world. Just a small amount of energy savings may contribute to saving the environment. Hydropower, one of the largest clean and renewable energy sources. Small hydropower systems are run-of-river schemes, which do not require a storage or dam to store water. So as we can see, Malaysia has the potential sites for hydropower plant because of high humidity, copious of streams and rivers, and hilly topography. Small hydropower systems are run-of-river schemes, which do not require a storage or dam to store water. TENOM-PANGI hydropower station is one of the small hydropower stations exists in the state of Sabah. So as we can see, this is the animation of the operation flow of SJHTP. Just a quick review of hydropower station that designed as run-of-river type. We have 3 units vertical axis of Francis turbine which can carry loads of 25 megawatt each. Currently, the total installed capacity is 75 megawatt. For now, there are problems faced by this station such as shaft seal frequently damaged due to a leak in sufficient flow rate and pressure for shaft seal cooling water system. In order to overcome this problem, there are some constraints should be considered, which is increase in pressure and flow rate will cause the shaft seal to float and leak and hard to do maintenance. The main aim for this project is to provide sufficient flow rate and pressure from the pump-in piping system in order to minimize leakage at the respected shaft seal. In order to achieve the main goal, we decided to be specific of our objective, which include to design and analyze piping system for turbine cooling water system in order to minimize leakage, to analytically determine the required number of pump and optimal operating condition in order to supply sufficient volume flow rate. And last but not least, to compare the performance of existing cooling water system with modified cooling water system. The present project is limited to the current cooling water system and pump in the piping system used at TENOM-PANGI hydropower station. This study will use analytical approach and numerical approach to gain results. SolidWorks software will be used for constructing the piping systems. The procedures for meshing and constraint the condition, selection of the simulation model, define boundary condition, setting up the convergence criteria and the solution through iterations, computing the results and graphic analysis will be done using the same software which is SolidWorks Flow Simulation 2017 software. Then, the Microsoft Excel will be used for analyzing data. The parameters need to be studied here are the pressure and the head loss in pipe and volume flow rate. Based on previous research on piping system, the investigation shows that it is important to have both pumps of the same capacity or having the same width impeller in order to avoid cavitation problems due to the first pump not supplying enough liquid to the second pump in series connection. For parallel connections, it is possible to have pumps of different capacity at different speed to produce a desired head with corresponding flow rate. In addition, centrifugal pumps in parallel are used to overcome larger volume flows than one pump can handle alone. When identical pumps are arranged in parallel, the flow rate will double compared to a single pump if head is kept constant. So, based on the first objective, the procedure on how to design and analyze piping system for turbine cooling water system in order to minimize leakage is by using numerical study, which SolidWorks Flow Simulation 2017 software will be used. The model of piping system were designed according to proposed design by using SolidWorks. And then we use SolidWorks flow simulation to do the pre-processing until post-processing. Specification of boundary condition and meshing process had been identified with specific solver setup. Based on the pump used by the company, the manometric head of pump is shown to be 25-meter head, which only can produce pressure of 2.45 bar. And this is the design modeling of the proposed design. Design modeling for the water tank are specified into height of tank with 7,000 mm, diameter of tank of 3,400 mm, and capacity until 10,994.48 liter. There are one inlet and two outlets. However, the modeling for 4-inch pipe consists of length of pipe inlet 1000 mm, height of pipe 2300 mm, length of pipe outlet 2350 mm, width of pipe of 5300 mm, and last but not least, length between pipe outlet is 12-inch. The 2-inch pipe was set to width of pipe 2500 mm, height of pipe 2500 mm, length of pipe 2500 mm as well. Size of pipe is 2-inch, and there are two ball valves with nozzle size of 0.5 inch. The inlet volume flow rate for tank and 4-inch pipe was set to 210 and 105 liter per minute respectively. However, the outlet for tank and 4-inch pipe was set to volume flow rate of 105 and 35 liter per minute respectively. The wall was specified to non-slip conditions and stationary. The inlet volume flow rate for 2-inch pipe was set to 400 kPa. However, the outlet was set to volume flow rate of 35 liter per minute. The wall was specified to non-slip conditions and stationary. The mesh generation finished normally. Mesh conversion tests have been done in order to ensure the accurateness of the results and procedure and produce unacceptable results. Comparison had been made between meshes to achieve high accuracy results. In this case, mesh 1 has been selected. The flow behavior of the piping system respected to pressure is shown as in the slide, expecting low pressure entering the pump and expecting high pressure at pump output and nozzle. To achieve our second objective, which is to analytically determine the required number of pump and optimal operating condition in order to supply sufficient mass flow rate, the requirements include volume flow rate must not be less than 35 liters per minute, and pressure at the output nozzle must be in between 3.2 to 3.5 bar. And the optimal operating condition that we need to take into account are the pressure at pump discharge and optimal volume flow rate required. So basically, this is the flow chart to do the analytical analysis in order to determine the required number of pump. First thing, we need to check the compressibility, and then we check the desired head for each unit, followed by determine the losses in pipe for H1, H2, and H3. Determination of delta H, which H desired equal to H real. Determine required head by the pump, which is head pump equal to head nozzle plus head loss in pipe. And last but not least, determine required number of pump. The compressibility of the flow has been determined, and it is found that the fluid flow is incompressible with Mach number less than 0.3. Next, we will check the desired head for each unit with corresponding to the requirement and constraints. Based on the slides, the desired head for each unit to obtain 3.2 bar to 3.5 bar are 32.62 meter head minimum and 35.68 meter head maximum. Friction loss in pipe also needs to be taken into account. So the Reynolds number has been calculated, and it is found that the fluid flow in the pipe is turbulent flow. The losses include pipe fitting for standard elbow, pipe exit, globe valve swing, as well as ball valve. So this is the continue of the calculation. It is found that the difference in head for HT3 is the lowest, and the difference in head for HT1 is the highest with value of negative 9.19 meter head. Hence, the required head for the pump are minimum of 36.46 meter head and maximum of 39.53 meter head based on the calculated value. Therefore, the suitable pump for the piping system is pump with 37 to 40 meter head and can supply 35 liters per minute of volume flow rate minimum. This is the current pump in piping system used for shaft seal cooling water system. We only have one operating pump that supply water for cooling water system at the shaft seal. Due to losses in pipe and the pump itself, the pump cannot supply sufficient volume flow rate and pressure to each turbine cooling water system. Therefore, it will cause wear shaft seal due to the friction of the shaft rotating. Thus, we will install pump for each turbine cooling water system to overcome insufficient volume flow rate and to supply enough pressure to the turbine. However, the service tank only support capacity up to 10,000 liters only. Hence, the pump located at the service tank should support large volume flow rate to avoid insufficient clean water. From the result obtained, the pressure for all three pumps has low differences, hence the pressure distributed evenly. Last but not least, we will compare the performance of existing cooling water system with modified cooling water system in terms of pressure output at the nozzle. The performance of proposed cooling water system exceeds the performance of existing cooling water system. From the simulation, the pump installed individually can support each turbine with minimum pressure of 3.65 bar and maximum pressure of 3.68 bar. As in conclusion, the objectives of this study were achieved. Design and analysis of piping system for turbine cooling water system has been developed successfully by using map-mesh method. Analytical analysis of pump in piping system and optimal operating condition has been determined in order to supply sufficient mass flow rate. The performance of existing cooling water system with modified cooling water system has been compared. And for the recommendation, instead of using SolidWorks flow simulation, use ANSYS Fluent to analyze the CFD analysis problem. And use RNG K epsilon so that the piping system can be simulated precisely. Transient time should be used rather than steady state time to study the behavior of water concisely with respect to time. And that's all for me, so thank you.